Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 7, discusses rotational spectroscopy of polyatomic species. There are a number of classification schemes for molecules. We will see in Masterclass 9 that symmetry classification based on group theory is perhaps the most useful method. Here, however, we will broadly classify molecules based on their moments of inertia about three perpendicular axes passing through the molecular center of mass. These axes are labeled the A, B, and C axes, and they are defined such that the moment of inertia about the C axis is the largest of the three axial moments of inertia. This is followed by IB, and IA is the smallest moment of inertia. Molecules in which all three moments of inertia are equal are known as spherical tops. Spherical top molecules are highly symmetric species, so they have no permanent dipole moment. As a result, spherical top molecules do not exhibit a pure rotational spectrum. Molecules in which two of the three moments of inertia are equal are known as symmetric tops. If the two largest moments of inertia are equal, the molecule is referred to as a prolate top. If the two smallest moments of inertia are equal, the molecule is an oblate top. Symmetric top molecules exhibit pure rotational spectra and have a relatively simple analytical form for rotational energies. We will explore these molecules in more detail. Most molecules are asymmetric tops, wherein all three moments of inertia are different. In some cases, like water or formaldehyde, we find that two of the moments of inertia have nearly the same value. Such species are referred to as near prolate or near oblate symmetric tops. In general, there is no simple analytical form for the rotational energy levels of asymmetric top molecules. In general, moments of inertia about three perpendicular axes give rise to the need for three rotational constants for our energy level description. As we saw in Masterclass 6, rotational constants are inversely proportional to the moment of inertia for diatomic molecules. The same is true for polyatomic species. Owing to the fact that IA is the smallest moment of inertia, the corresponding A rotational constant has a value that is, in general, larger than B, which is in general larger than C. Here, however, rotational constants no longer explicitly relate to individual bond lengths, since bonds are not typically aligned directly along or perpendicular to the A, B, or C axes for polyatomic species. Still, through measurement of rotational spectra, molecular moments of inertia can be deduced, which in turn may be used to precisely determine molecular geometry. For symmetric top molecules, two of the moments of inertia are equal, which means only two rotational constants are required to describe rotational energy level structure. For prolate top molecules, where IB equals IC, we use the A and B rotational constants. Owing to the reduced overall symmetry of symmetric top species, two quantum numbers are needed to specify how a molecule is rotating. The total angular momentum quantum number, J, defines the overall rotation of the molecule, while the symmetry axis projection quantum number, K, defines the rotation about the symmetry axis. For prolate tops, K describes rotation about the A axis. If all the rotational motion of a prolate top is about the A axis, then K equals J. If none of the rotational motion of a prolate top is about the A-axis, then K equals 0. Since two quantum numbers are required to describe the rotational motion of a symmetric top, rotational energy levels are labeled with the J value and a subscript K value. We also find that the J and K quantum numbers arise in the energy level expression for symmetric tops. As usual, J can take any positive value, or 0. K, on the other hand, must take values that are integer steps in the range from J to negative J. As usual, each level has a 2J plus 1 degeneracy under field-free conditions arising from the M sub J spatial projections. We also find that each level with K greater than 0 has a twofold degeneracy. This is apparent if we compare the J equals to K equals 2 motion with the J equals to K equals negative 2 motion for chloromethane. In both cases, rotation of the molecule is entirely about the symmetry axis. Thus, both motions have the same atoms moving about the same body-fixed point in space, with the same moment of inertia and therefore the same rotational energy. In other words, for each clockwise rotation about the symmetry axis, there is an equivalent counterclockwise rotation. The description for oblate tops is very similar to that of prolate tops. For oblate tops, both J and K quantum numbers are needed for a unique description of the rotational motion, and energy levels are again labeled as J sub K. Each J level has a 2J plus 1 degeneracy under field-free conditions, and each K level with K greater than 0 is doubly degenerate. In this case, though, the unique rotational axis is the C-axis, and the unique rotational constant is the C constant. In comparing the energy level structures of prolate and oblate tops, we see major differences. For prolate tops, the A rotational constant is larger than the B rotational constant, which results in a positive value for the K squared term in the energy level expression. Thus, for a given J value, prolate top level energies increase with increasing K. For oblate tops, the C rotational constant is smaller than the B rotational constant, which results in a negative value for the K squared term. Thus, we find that for a given J value, oblate top energies decrease with increasing K. In Master Class 6, we learned that molecules must possess a permanent dipole moment to be rotationally or microwave active, and that delta J must be equal to plus or minus 1 to account for conservation of angular momentum upon absorption or emission of a photon. For symmetric top molecules, transitions must also obey a delta K equals 0 selection rule. As usual, the delta K selection rule arises from our treatment of the transition dipole moment, and it can be viewed as a consequence of symmetry and conservation of angular momentum. Given the selection rules for J and K, we find that allowed transitions for symmetric tops within the rigid rotor approximation occur at 2b times J plus 1. We therefore expect spectral lines to occur at 2b, 4b, 6b, etc., with line spacings of 2b. This, of course, is similar to our findings for linear molecules. In other words, if symmetric top molecules were rigid systems, we would obtain no information concerning rotation about the unique axis. The concept of centrifugal distortion was also discussed in Master Class 6. For diatomic molecules, we saw that centrifugal distortion results in a stretching of the internuclear bond, thereby effectively reducing the rotational constant and compressing the energy level structure. For polyatomic species, bonds and bond angles are distorted by the centrifugal force associated with molecular rotation. To account for these geometry changes in symmetric tops, 3 centrifugal distortion constants are required. One that describes the distortion about the symmetry axis, d sub k, one that describes the centrifugal distortion as a function of overall molecular rotation, d sub j, and a cross term, d sub jk, which describes the coupling between rotation about the unique axis and the end-over-end rotation of the molecule. By accounting for the effects of centrifugal distortion, we find that there is now a k-dependent term in our expression for calculating transition wave number. Thus, we see that there are distinct spectral lines associated with different values of k for a particular delta J of plus or minus 1 rotational transition. As was the case with atoms, molecules too can interact with external electric and magnetic fields. We saw in Master Class 4 that such interaction lifts the 2J plus 1 state degeneracy of a level due to space quantization. Microwave active molecules can interact with external electric fields to lift state degeneracy via their permanent dipole moment, which is a molecule-fixed electric field. By determining the component of the permanent dipole moment that points along the total angular momentum vector, and the projection of the J vector onto the external electric field, we can calculate the Stark energy of interaction. Thus we see that the Stark energy is not only dependent on the molecular dipole moment and the magnitude of the external electric field, but also on the K, J, and M sub j quantum numbers. In other words, the Stark splitting exhibited by each quantum state is different. Note also that the Stark energy is inversely proportional to J squared. As a result, Stark splitting quickly decreases with increasing molecular rotation. The effects of nuclear spin are an important consideration in spectroscopy. Nuclear spin can affect the energy level structure of a molecule in 2 ways. First, like electron spin, nuclear spin gives rise to a magnetic moment. The nuclear magnetic moment can interact with the electron magnetic moment to give rise to hyperfine splittings in spectra, and it can interact with external magnetic fields to lift nuclear spin state degeneracies. The topic of hyperfine spectral splitting will not be covered in Chemistry 209. The interaction of nuclear magnetic moments with external fields, however, forms the basis of NMR spectroscopy, which we will discuss in more detail in master classes 13 and 14. Here we are interested in how nuclear spin affects the statistical weights of rotational wave functions, since molecular rotation can potentially exchange identical particles. First, recall that bosons are particles with integer spin, and fermions are particles with half-integer spin. Since both protons and neutrons possess a spin-angular momentum of I equals 1/2, we find that even-mass nuclei are bosons and odd-mass nuclei are fermions. Now, recall the Pauli exclusion principle, which can be stated as any acceptable wave function must be antisymmetric with respect to the exchange of two identical fermions and totally symmetric with respect to the exchange of identical bosons. The importance of nuclear spin is apparent when we view the total wave function as a product of the electronic, vibrational, rotational, and nuclear spin wave functions. Here we see that the total wave function symmetry depends on the symmetries of each of its component wave functions, including the nuclear spin wave function. Consider, for example, the nuclear spin wave functions for molecular hydrogen. The nucleus of each hydrogen atom is a single proton, so each nucleus is a fermion with I equals 1/2. The nuclear spin angular momenta can be aligned with or against an external magnetic field. We describe this alignment with the projection quantum number m sub I, which can take the values of positive or negative 1/2 for our hydrogen nuclei. These projections may also be referred to as alpha and beta spins, or as spin-up and spin-down nuclei. Thus we see there are four possible orientations of the two hydrogen nuclear spins, both alpha, both beta, alpha-beta, or beta-alpha. By taking a linear combination of the latter two spin functions, we see that there are three nuclear spin wave functions that are symmetric with respect to nuclear exchange, and one that is antisymmetric with respect to nuclear exchange. This, of course, is the same treatment that we use to describe electron exchange in Master Class 4. Since we are concerned with the exchange of fermions, the total wave function must be antisymmetric with respect to permutation of the hydrogen nuclei. However, the H2 ground state electronic and vibrational wave functions are totally symmetric. Therefore, the product of the rotational and nuclear spin wave functions must be antisymmetric. A closer examination of the rotational wave functions shows that even J levels are symmetric upon 180-degree rotation, whereas odd J levels are antisymmetric. Thus we find that to satisfy the Pauli exclusion principle, even J wave functions must be paired with antisymmetric nuclear spin wave functions, and odd J wave functions must be paired with symmetric nuclear spin wave functions. As a result, for H2, odd J rotational energy levels have 3 times the statistical weight of even J levels, and rotational transitions originating from odd J levels have 3 times the intensity of transitions originating from even J levels. Owing to the Pauli exclusion principle, nuclear spin statistics are an important consideration for any rotational motion that exchanges indistinguishable particles. Here we have demonstrated this for a simple homonuclear diatomic molecule, but similar effects are observed for polyatomic species like water, where 2 identical hydrogen atoms can be exchanged by rotation, or ammonia, where 3 identical hydrogen atoms can be exchanged. See you next time.